All right, so jumping into our first real dynamics question using position vectors. So basically we're given this position vector, which describes the displacement of a particle with respect to time. And our first question is find expressions for the velocity and acceleration vectors at time t seconds. So basically we're deriving that and then finding the second derivative of that as well. So nothing too difficult, I hope. So here's our initial vector. The vector r with respect to t is equal to 4ti plus 10t minus 5t squared j. Now we can use our newly found time derivative notation. So this is the change in displacement over time, otherwise known as velocity. And really we're just finding the derivative of 4t, which is 4, because it's the derivative of 4t with respect to t. And then the derivative of 10t minus 5t squared, which is just going to be, 10 minus 10t j. Okay, so this tells us our displacement with respect to time. This tells us our velocity with respect to time, and we can go one step further. There's an r, t, 2 dots this time. So this will be our acceleration vector. So the derivative of 4, so we're going to lose an I component altogether. So there's no acceleration in the I component of our vector, but there is going to be an acceleration here. 10, that's going to derive to 0, minus 10t, that's going to be 10. So it's simply 10j. That should be a j. Minus 10j, I should say. Okay, that makes sense. And you're probably going to see that a lot. That's pretty close to 9.8, which is our gravity constant. So this could be a particle sort of falling through the sky of some sort, perhaps. Okay, but there's find expressions for the velocity and acceleration. That's the first step here. Determine the initial position and speed of the particle. That's going to be pretty straightforward, I think. So if we want the initial position of, so there's two questions here, the initial position and the initial speed. So if we want the initial position, we just need to let t equal 0 and put it into this function. So r0 equals 4 times 0 I plus 10 times 0 minus 5, 0 squared, and that's going to be our j component there. A great surprise here that's going to be 0. So the initial position is the origin. This happens pretty frequently. A particle starts from point 0, 0. Now, the next part is a bit of a trick question here because it says, and then find the speed of the particle. Now, if you want to know the speed of a particle, you don't you can sub it directly into our velocity function here, but that's going to give you a velocity in the I component and a velocity in the j component. So if you want the actual velocity, you don't want to know the velocity in each individual component. You want to know the magnitude of this vector. You want to know how much in total is the speed. Doesn't matter what direction the speed is taking place in. So it's not just going to be the velocity vector with t equal to 0. It's going to be the magnitude of that. So if we sub that in, we'll have equals 4 plus, I'm leaving the i's off for a second, you'll see why, and then 10 minus 10 times 0, so that's going to be 10. And then I'm going to have to square both of those and square root. So really I'm finding the magnitude of our vector, which you've done before. And so that's going to be 16 plus 100, the square root of 116, which if you put that into or if you simplify that third, 2 root 29. Okay, so the the speed of this particle is about 10.5, and then just look at our units, meters per second. Meters per second. Okay, so just be careful when you're finding the speed of a particle, it's the magnitude of your velocity vector. All right, so next up, when t equals 4 seconds, calculate the distance of the particle from the origin. Okay, so part C. So our particle is somewhere, some distance from the origin. Now this is different to finding the position. If we wanted to find the position, we just sub 4 back into our equation here. But we don't want to find the position, we want to find the distance. So we're doing essentially another magnitude question here. So it's going to be R4, still using our displacement vector, not our velocity vector, because we want to know how far we are from the origin. And then we're summing it in equals 4 times 4i plus 10 times 4 minus 5 times 4 squared j. This gives me my position, which is 16i minus 40j. But if I want to know my magnitude, which is what my distance is from the origin, it's going to be the square root of 16 squared plus minus 40 squared. That'll be 8 root 29 by the time you simplify it. Okay, so there's my magnitude. Now the next question gets slightly harder though, because it says the velocity, both magnitude and direction of the particle at time equals 4 seconds. So we need to do two things. We need to find magnitude, which is an identical calculation to what we did here, but we also need to find direction, which is only slightly more challenging, I suppose. So jumping into it back over here. So now we need r dot, because we're working with velocity now. 4. Now we sub that into our velocity vector. So it's going to be 4i plus 10 minus 10 times 4j. And then we find the magnitude of that. So it's going to be 4 squared minus 30 squared, adding them together. Probably don't need that one there. And then square root of both. And so that'll be 2 root 229 meters per second. So that's my the magnitude. Essentially, I found my speed here, but I don't know what direction the particle's going in. But I do know where the particle is. Where it is doesn't really help me much in determining its direction, its immediate direction right now. But what does help me is knowing that at R4, my velocity vector is 4i minus 30j. Now, the way that you interpret that is it's moving 4 units in the I direction, and it's moving 30 units in the j direction at that specific time, in that immediate instant. So I'll sketch that really quickly. So 4i, 1, 2, 3, 4, minus 30j down here somewhere. So that point is 4i 30j, where that's an I and that's a j. Now that's not the position of my vector, that's the direction in which it's moving. So in order for us to sort of talk about direction in a meaningful way, we don't talk about 4i 30j about direction. If I knew this angle here, then I would know what direction this thing was moving in. And that's going to be really, really straightforward. We're just talking about trigonometry now. So if I can find that angle, it's going to be like tan theta equals 30 over 4. And that should be 30 over 4, not 40. Negative 1, 30 over 4. Find out what that angle is. So that gives us like 82 degrees and 24 minutes. So now we're really finished answering that question. We know the velocity. It's traveling at 2 root 229 meters per second in a direction of 82 degrees 24. You could talk in terms of north of south or south, sorry, you could talk in terms of south of east if you wanted to, but that angle should be enough, I think. So then the last part of part C asks for the measure of the angle between the velocity and displacement vectors. So you might really have to stretch your brain here to remember that to find the angle between two vectors, you can use like a dot product between the two vectors. So if I do the dot product of R4 R dot 4, so the dot product between the velocity and displacement vectors, I should be able to get myself an answer. Say that R4 dot R4 is equal to the magnitude, and you should remember this, I hope, 4 times the magnitude of dot 4, which is our velocity vector, times the angle between them. Okay, so maybe just a really quick dot product recap. If you want to find the dot product between two vectors, two ways to do it. Either you multiply the I components by the I components and the j components by the j components, and you add them together, or you take the magnitude of one, you multiply it by the magnitude of the other, and you multiply it by the cosine of the angle between them. So that's really, really quick in a nutshell, but we can't be spending time on that. Now what we can do now here, because we can multiply the I components by the I components and the j components by the j components, because we know them both, and because we know the magnitudes of this and this, we can rearrange this equation to find cosine theta, because we know that this is going to be 16, and this is going to be 4, so we can do 16 times 4 plus, and then we have negative 40 times negative 30. And then on this side, we've got the magnitude, which is 8 root 29, times the magnitude, which is 2 root 229. And we're going to multiply all of that by cosine theta. Then we can rearrange this and find out what theta is. So we can say that cos theta equals all of that divided by all of that. Be 1264 over 16 root 6641. And then if we just do like an inverse cosine here, we can say that theta is equal to 14 degrees and 12 minutes. So the angle between the velocity and displacement vectors is 14 degrees and 12 minutes. Finally, the very last question will take 20 seconds. Is the acceleration constant for this motion? Well, the acceleration is negative 10 in the j component. So yes, it is constant. There's a constant there of negative 10. So yes, absolutely. Not much more than a sentence there to explain why the acceleration is constant. It's only if there's a function in there where the displacement and the velocity were not constant because of those. Okay, that's a lot of stuff there on dynamics using position vectors.